In this video, we're going to show you how to use Python to control Serial Wombat chip, embedded coprocessors, and smart I/O expanders. It's an exciting time here in July of 2026 for Python on the Serial Wombat chip. For the first time ever, it is fully caught up with all of the capabilities in Arduino. And a lot of that has to do with the power of ChatGPT, which has helped me much more rapidly do some of these conversions, and even found a couple of bugs in my protocol that I ported the fixes back to Arduino. This video supersedes all previous Python videos. Those will all be marked as deprecated. There's a matching user guide that will show all of the various commands that I send in Raspberry Pi and others that is available in the links below. Over time, this video will likely change. If it's marked as deprecated in the title, then look in the links down below for the most recent version. And it's possible I may have a few add-on things as things happen in the future. If so, those will be in the links as well. So if you don't find the answer to your problem, look in the links down below and perhaps it's down there. This is the third major update of Python libraries. This one structurally is quite similar to the others. The big difference is how we implement interfaces. Python comes in three major flavors that we support: CPython, which is your regular Python that runs on a PC or Raspberry Pi, Micropython, and CircuitPython. And then on top of each of those, you may interface to the Serial Wombat chip either with I2C, with UART, or with a UART to I2C bridge running on something like a Arduino shell or something like that. So we're going to walk through how to connect up to each of those different platforms. And we're also going to talk about Raspberry Pi, how the early versions 4 and earlier didn't properly implement I2C clock stretching and the workaround for that. We will also demonstrate how to do firmware updates on the Serial Wombat 8B and the Serial Wombat 18AB from different Python platforms. The Serial Wombat Python library is a layered library. At the very bottom is an interface file, and that interface file is used to hand off packets to and from the Serial Wombat chip. And maybe that's over UART, maybe it's over I2C, maybe it's over a UART to I2C bridge. In the future, it's possible we may also support sending packets over TCP/IP or something like that. And all of that is abstracted. When you're on a particular platform, you're going to pull in that interface file. The interface file has an area where you're going to customize it. If you're on a Windows PC, you may have to specify which COM port you want to use. If you're on Linux, you may have a TTY that you're going to connect up to. If you're on Micropython, you may specify which pins are your I2C, SDA, and SCL. Once you do that, there's a higher level function that creates the Serial Wombat chip instance. So we have the bottom layer, which sends and receives packets. On top of that, there is a Serial Wombat class that the interface class inherits from, and it provides all of the functionality of the Serial Wombat chip: reading the source voltage, looking at memory locations, getting the version, on the Serial Wombat 18AB, getting the temperature. The Serial Wombat chip has a variety of pin modes that run at 1 kilohertz. Each one is its own state machine. There is the Serial Wombat pin class. It handles things like setting or retrieving the public data for that pin, and generic pin functions like, say, setting them to be weak pull-up or open drain, things like that. Then each pin mode inherits from the Serial Wombat pin class. So that's how you take a pin and you say, okay, and we're going to turn it into an analog to digital pin, or we're going to turn it into a PWM pin or a servo pin or whatever. And so each of those pin mode classes is in a separate file. Additionally, we need some generic functions that delay a certain number of milliseconds or delay a certain number of microseconds and some other things, yield the processor. For each platform, CPython, Micropython, and CircuitPython, there's an Arduino functions.py file that you'll pull in. Those implement the delay functions the same as they are on Arduino, so that it makes for really easy code porting and comparison between the Arduino code and the Python code. The interfaces for Python and Arduino are virtually identical. all of the same class methods and parameters, return values. The only difference is minor changes in how Python hands things back. For instance, in Arduino, we can hand values back by reference. We don't do that in Python. You hand back a list and then break up the list. So some of those things are a little bit different, but effectively they are exactly the same. So if you go to the Serial Wombat Arduino library GitHub docs, there is extensive documentation on each of these classes and their interfaces. All of that is 100% applicable to your Python code, and so I didn't try to duplicate it, having multiple different docs anywhere. Going forward with version 2.2.5 and later, I will only release a version when the Python, C#, the protocol analyzer, and the Arduino are all in sync with each other. That's when the release will go up. So now let's take a look at Python under Raspbian on the Raspberry Pi. In this example, we're going to set up a Raspberry Pi 5. The Raspberry Pi 5 is the first of the Raspberry Pi boards which supports I2C clock stretching, which is essential for the proper operation of the Serial Wombat protocol. On prior versions, the chip was made by Broadcom, and they didn't fully implement the I2C spec, and so that meant that there needs to be a workaround. And we'll talk about that for the Raspberry Pi 4 and earlier in the next section of the video. So in this version, we're going to image the Raspberry Pi, and I'm going to set it up to SSH into it. I like to use my notebook computer and then have the notebook computer do Wi-Fi sharing for a lot of my Raspberry Pi stuff. Makes it easy for me to have something to connect to, even if I'm mobile, working in a coffee shop or whatever, playing with my Raspberry Pi. So we're going to do that. You can see here I'm writing the image. We finished that up, and I will boot the Raspberry Pi. We are connected to a Serial Wombat 8B, and it is connected up to the 3.3 line, the ground, the SDA, and the SCL. And on the Raspberry Pis, the SDA and SCL lines already have pull-up resistors, so we don't need to enable those on the Serial Wombat chipboard. So let's SSH into the Raspberry Pi now. And we're going to do some initial configuration of the device in order to make it work properly and to facilitate accessing it. So we're going to use the sudo raspberry config command, which will bring up the configuration tool. And the first thing that we're going to do is shut off auto login, because auto login can cause a problem sometimes where we have conflict for hardware devices. And so once we do that, we will exit out of the config tool, and we'll need to reboot the Raspberry Pi. We also want to enable the I2C interface. Next, we'll make a Serial Wombat directory where we can work, and we're going to clone the Broadwell Consulting Serial Wombat Python library. Now, I did a reboot offline, and now we can do an I2C detect -Y1. And what that does is scan the I2C bus for attached devices, and we see the Serial Wombat 8B chip, which is currently at address 0x61. Next, we'll clone the Serial Wombat Python library and create a directory for examples. In each directory where you create a new project, you're going to want to copy the Serial Wombat .py file, and then the appropriate interfaces for your platform, whether that's CPython, Micropython, CircuitPython. In this case, we're using CPython because that's what you use on the Raspberry Pi. And we're going to copy everything from the SMBus2 example interface directory to our example. And we also need the Arduino functions.py file that gives us delay functions most primarily. Now we're going to go into, we're going to copy serial wombat.py into that directory and execute that file. and we get an error. Because we didn't set the address of the Serial Wombat chip that we want to talk to in the example. So let's go into that example and put your Serial Wombat address here to the address that we saw on the I2C detect utility, which is 0x61. We'll exit and quit, and then let's run that again in Python. And it's working. We can see that it found a Serial Wombat 8 board, firmware version 224. The supply voltage is 2.23 volts, which is great. And it starts pulling the sequential public data number 0, 1, 2, 3. That's coming off the Serial Wombat chip. So that is fantastic. Next, let's create an example where we use a rotary encoder on the Serial Wombat chip. So we're going to copy from the examples directory the most basic quadrature encoder example. Then we'll go in and edit that example because we need to set up the proper pins that we want to be able to access. We set the address at the top of that. Again, it will use the quadrature encoder pin mode. We had to copy that in. And we come down here and we say we have the quadrature encoder on pins 2 and 3. So that's how we will attach them to the Serial Wombat chip. When we get into the loop, it will periodically read the quadrature encoder and output the position of the quadrature encoder. We'll execute that now, and we can see it running. And as I turn the knob, we can see that it moves. And so everything is working really, really well here. So that's the end of our example for the 5. Now let's take a look at what it takes to do I2C communication on the Raspberry Pi 4 and earlier. Raspberry Pi 4 and earlier had a flaw in the Broadcom chips used as the main microcontroller, which did not properly implement I2C clock stretching in hardware. And that was kind of a showstopper because the Serial Wombat chip relies on that part of the I2C spec for its communication. Fortunately, there is a workaround. We can do something called an overlay, where we have it use a software-driven I2C implementation on the same pin, and it looks pretty much the same from an OS standpoint. So we're going to do the same thing we did on the 5. We're going to disable automatic login, and unlike the Raspberry Pi 5, on this Raspberry Pi Zero that I'm using as an example of the earlier boards, we're going to make sure that I2C interface is disabled because we're going to use a software overlay. So we're going to reboot. That'll take a second. And I paused time, and now we're back in after the reboot. And let's change direction to /boot/firmware. And all of this is in the guide that is linked to down below in the comments. We're going to do sudo, because we're modifying an operating system file, sudo vim config.txt. And we're going to come in here and we're going to add a line for a DT overlay on the I2C using software GPIO. And I'm not going to type all of this out. Again, go to the file that I linked to down below, and you'll be able to simply cut and paste it into your shell into the file. Note that in this file, we are choosing GPIO2 as SDA and GPIO3 as SCL. You could theoretically do others, but it really makes sense to use the ones that are allocated as I2C hardware in a lot of cases, because those already have pull-up resistors on them within the Raspberry Pi. Once we make these changes, we will do a reboot. And again, I pause time. And then I'm going to reconnect. And we'll create, as in the prior Raspberry Pi 5, we'll create a Serial Wombat directory that we're going to work in. We'll clone the Serial Wombat Python repository. And then we are ready to create our example directory and start copying in the files that we need. As always, the Arduino functions .py, the Serial Wombat interface. We'll be using the same CPython SMBus2 I2C. And then we will copy in the example from that interface directory and also the serialwombat.py file from the root directory of the repository. And we'll run I2C detect again, as we did with the Raspberry Pi 5, and we see that the software I2C was successful at being able to find a device at 0x61, which is where our Serial Wombat 8B is located. So now we're going to go into the example file and change the address to 0x61, which is what we saw in I2C detect. And then we will run this example. And again, it works. We see Serial Wombat in 8B, firmware version 2.2.0, and 3.27 volts of supply voltage, and it is pulling a sequential number out of one of the public datas. So that works great. Another great connectivity method is using the Serial Wombat 18AB's UART mode along with an FTDI or other UART to USB converter. In this case, we've taken an 18AB and plugged an FTDI cable into the USB port, creating TTY USB 0 on the Raspberry Pi. We're going to run the exact same example that we did in the past, only in this case, we're going to copy from the CPython interface /serial, and note that that's serial and not serial bridge, and run the same thing, showing that we can do this. Note that in some cases, you may have to add permissions for the user that you are to be able to access the TTY serial ports, and there is instructions on that in the user's guide down below. So let's do the same thing that we always do. There's always at least 4 files that you need. Your actual script that you're running, in our case, that's example 1, the Serial Wombat interface file from the platform and interface type that you want. In this case, that is the CPY_serial version, and then the Arduino functions. Now we're going to come in here. This example wants you to set a COM port. And so in this case, since we're on Linux, we're going to do /dev/TTY USB 0. Then next we'll edit example, and we don't strictly speaking need an address, but the Python script won't compile without it, and we use the same example script regardless of the interface we're using, so we'll call it 0x6b, which is what it would be if we were on I2C, even though we're not. So then we do the same thing, python example.py, and we get the exact same output that we've seen before, except this time the model is an S18 instead of an S08, and this particular Serial Wombat 18AB has firmware version 2.21 in it. So same thing as all of the rest. Basically, those 4 files get you started. When you run examples, you may get a message that you're not on the latest firmware. New versions of the Serial Wombat firmware come out periodically that fix bugs and add great new functions. So you may want to do an update. And that's very easy in the Serial Wombat Python. It is simply a script that you run, and you have to copy the hex file of the image that you want to upload into the same directory. So in this case, we're going to do a git on the Broadwell Consulting Inc. Serial Wombat repository, in addition to the Python repository, so that we get the hex files that we need. Now we're going to create another project directory. In this case, we'll call it BL08 because we're going to bootload a Serial Wombat 8. And we need the same files that we always do. In this case, we're going to be connecting over I2C, so we're going to use the CPython SMBus2 interfaces. We need serialwombat.py as always, and we need the Arduino functions. And then we're going to copy from the examples directory the Serial Wombat 8 firmware update sketch, and we will copy one of the firmware.hex files from the Serial Wombat firmware repository. So now let's do a quick look again at this directory, at everything that we have in here. So we've got the Arduino functions, Serial Wombat 8B hex file that we want, the interface, and the Serial Wombat. The last thing we need is the actual script that does the downloading. We'll get that out of the examples directory. And so we'll need to modify the bootloader script to tell it what address we want to bootload. And in this case, I had edited this previously, so it's already set up for our 0x61 under SW address. Note that the script will download the very first file that it finds in the directory that ends in .hex, so you want to make sure only the file that you want is in the current directory. Now we're going to say Python bootload Serial Wombat 8B. It's going to jump to boot. It found it. Version 2.04 is the bootloader version, and it erased the flash, and now it's downloading the new flash. And that's it. It sets the jump to app flag and resets. Now, if we would run example again, we would see that we got an update to the new version. For Micropython, you can have a variety of different microcontrollers. I assume that you are using an RP2040, and that you're using the Seed Shao. I love the Shao boards, and we have a Serial Wombat 8B and 18AB extension boards that are specifically designed to work with those. So you can see the board that I'm using right here that has the RP2040 in it. We're going to be using Thani under Windows as our Python development environment. And what I did was I created on a drive, on my drive Z, I created Python example, and we're going to copy the files that we need into that directory. And you need Arduino functions, the actual script that you're going to want to run. In this case, that's example.py, serialwombat.py, and then the Serial Wombat interface file that you use. In this case, we are using the Micropython I2C. And so you can see if you go into the interface file, that gives you the option to set the pins that you're using. When you go into your example, you need to set the address. On the case of the Shao board, it's 0x63. And if we run the example, we can see that, okay, it found a Serial Wombat 8B board version 2.24. The current power is 2.342 volts, and it starts pulling the sequential numbers. There is another file called Serial Wombat chipfinder.c that will look on the I2C bus for all devices and try to guess if they're Serial Wombat chips or not. And we saw in that case it did a successful download. And we see in this case it found two Serial Wombat chips on the Shao board at 0x63 and 0x64, which is what is expected. CircuitPython and Micropython work essentially the same with regard to the Serial Wombat chip. You can see here we're going to load the CircuitPython executive onto this RP2040 SHAO board that we're using with a Serial Wombat SHAO expansion board. This board has two Serial Wombat chips. It's at address 0x63 and 0x64, and so we're going to try to talk to the one at 0x63. Once the executive is loaded, we will go into Thani and connect up to that board. In the previous example, we'd already created a directory that had the Serial Wombat Python files in it, but in order to talk to CircuitPython instead of Micropython, we're going to go into the CircuitPython directory in the repository and drag in the Serial Wombat interface and Arduino functions that are appropriate for CircuitPython. Once we've done that, we will load them up to the board in Thani. And then launch example.py, and we can see that run. We didn't define the address, so we're going to go up here and we're going to tell it, make it 0x63, which is the first chip on the SHAO expansion board. Hit go, and we can see that we connect up to the Serial Wombat 8B chip, and we see it has version 2.24. So that works good. As with the Micropython, there's a Serial Wombat chip finder example. That Python sketch finds all of the Serial Wombat chips, and on this board there is one at address 0x63 and one at address 0x64. Updating firmware is easy using CircuitPython. We're going to use the example that we did in the previous video segment, and we're just going to drag the Serial Wombat 8B firmware update sketch out of the examples directory in the Python repository into our project directory. And then we're going to go into the Serial Wombat repository, which is the firmware repository, go into Serial Wombat 8B, releases, and that is where all of the hex files are located. So in this case, let's downgrade to version 2.23, and we will pick the 2.23 default.hex, go into Thani, and now we're going to have to load those files onto the CircuitPython board. So we'll right-click and say upload. Then we open up the firmware update sketch. We're going to change the address to what we want to, in this case, 0x63 for this board, and hit go. And we need to set the address there, 0x63. It will process the hex file. Takes a couple of seconds, and this is the latest version because we were going from 2.24 down to 2.03. We confirm that. It says OK. It's going to erase flash, and then it's going to write all of those items into all of the lines of flash into the Serial Wombat chip and set the jump to app flag. And then at this point, we can go back to the prior example or the Serial Wombat chip finder, and we say, oh yeah, look, now the chip is at version 2.23. Another common way of communicating with a Serial Wombat chip is by a device that acts as a UART or USB to I2C converter. Under Arduino, there is a sketch bridge 115 to I2C with addressing that can be loaded into a board, such as the Arduino that we're seeing here. This is an Arduino Uno. And the purpose of that is to convert from the USB that comes into the Arduino into I2C. And with this, you can actually address multiple different Serial Wombat chips over a single I2C connection, which is a little bit different from how we connect up using the native UART capability on the Serial Wombat 18AB. So just like everything else, we're going to use CPython here, and we're going to do that from a PC. And we're going to copy in the Serial Wombat interface from CPython, Serial Wombat CPy serial addressed, along with the Arduino functions and the example sketch. And we will open this up in Visual Studio Code. I have the Python extensions added to Visual Studio Code, and we will say run and debug on this. And as always, we have to put in the address of the Serial Wombat chip we want to talk to. In this case, it's 0x60 for the Serial Wombat 8B PCB29 chip. And we hit go. And once again, we see a Serial Wombat 8B with firmware 224. And we're seeing about 5 volts, which is what's coming off of the Arduino. As in prior examples, we can also use the Serial Wombat firmware update script for the Serial Wombat 8B, and we're going to make sure that we have a copy of the firmware file in that directory, and we will run that here. It says it already has the latest version. Should we proceed, we'll say capital Y. It'll put the chip into boot mode. It will erase the flash and write the new image into the Serial Wombat chip. You can see that it runs a little bit slower here compared to other versions because the bridge adds extra latency as it gets the packet over UART, sends it out over I2C, gets it back, then sends it back over the UART. Finally, let's look at one more example where we are going to connect to a Serial Wombat 18AB chip using UART directly. This is exactly the same process that we used on the Raspberry Pi to connect up over UART there. It just will have a different name for the UART. And as before, we copy a serialwombat.py file, the example file, the Serial Wombat interface, in this case from Python Serial, and the Arduino functions.py. We're also going to want to get the firmware update sketch for the Serial Wombat 18AB from the examples area in the Python repository. And then we will go back to the Serial Wombat firmware repository to grab a firmware image that we want to load into the Serial Wombat chip. In this case, let's load the version 2.21. That's an old one, no reason to really do it, except we're doing it for an example here. So we'll right click and we'll say open this in Visual Studio Code. We can see the files we have here, Arduino functions, example, Serial Wombat interface. We're going to go in here and give it the COM port number for the FTDI cable that I'm using. In this case, on my computer, it assigned it to COM9. And we will hit run and debug on the firmware update script. It says, oh, we're already on the latest version. Hit Y to continue. And it'll jump to boot and start the firmware. So I'm showing this at 25 times the normal speed. Updating the Serial Wombat chip 18AB takes a while, and even more so over a bridge. So when it finishes that, it calculates the CRC, makes sure that that's correct, and then programs the last line of flash, which says we have a valid app, and then it will jump. Again, we have to put in the address into the example for the Serial Wombat 8B chip. That is 0x6B by default. And we'll run that again. And we can see that the chip was downgraded to version 2.21 of the firmware, so that worked good. Well, that took nearly 30 minutes to go all the way through. So hopefully you're fully versed now on how to use Python with the Serial Wombat chip. Check down below to make sure there are no addendums, corrections, or additions with this. And again, if this video is marked deprecated, then take a look down below to get the link to the new one. Until we talk again, have fun, keep making stuff.